This is The Future Of, where experts share their vision of the future and how their work is helping shape it for the better.
I'm David Blaney. Space exploration has led to a greater understanding of planet Earth, our solar system, and our place in the universe, but there's still much to be discovered. To help uncover some of the greatest cosmic mysteries, space agencies around the world are planning missions to explore neighbouring planets, photograph our own planet, and even search for extraterrestrial life. To discuss the future of space exploration, with me today is Professor Phil Bland, who leads Curtin University's Space Science and Technology Centre and is one of the joint winners of the 2019 Scientist of the Year Award. Thank you very much for joining me today, Phil.
Great to be here.
Have we gotten any closer to discovering life beyond Earth? Bit of a big question to begin with.
That is a big question to begin with, yeah. So I would say that we are actually kind of the first generation that will find out, we might not discover it, but we'll find out how lonely the universe is. We'll be able to, I think within the next 20 years, we'll have a pretty decent idea if there's been life on Mars. Within the next 30 or 40, whether there's any traces of anything on the icy satellites around Jupiter and Saturn. And what's kind of wacky is that really any day now, we're almost at the point where we have enough resolution in telescopes to be able to image individual Earth-sized planets around other stars. And when we can do that, we can actually get an idea of what their atmosphere is made of. And life shifts the composition of an atmosphere of a planet. So life is, so an atmosphere of a planet, basically, you can tell just by looking at it from 50 light years away whether that planet has a big biosphere or not. So it's kind of wacky, but it's within, maybe not now, but within a couple of years, literally a couple of years, there's the potential that that'll be the morning's news, that we've discovered a biosphere on another planet, which would obviously change things quite a lot about
quite horrifying news.
Yeah, oh no, it'd be fantastic. What do you mean? That'd be awesome. It would instantly become, the focus of, a massive amount of research. But within, a couple of decades after that, we would have done that enough times to planets that look like good candidates for life, that we would be able to say, okay, maybe it's not as common as we thought. Maybe it's more lonely than we thought, which would be interesting.
Which is equally horrifying. Either way, it's horrifying.
I don't like the idea that it's lonely. Yeah, I like the idea that there's lots of stuff out there. So, yeah.
And you mentioned telescopes that can look at planets orbiting other stars. Is that within our own galaxy, or is that also in other galaxies as well?
Yeah, that's within our own galaxy, and it's fascinating. I mean, it's fascinating for me. When I was undergraduate, we didn't know whether there were other planets we didn't. Maybe the only planets in the universe are the ones orbiting our sun, and now it's 6,000 that have been discovered. So many that we think that, there are certainly more planets in the galaxy than there are stars, that it's just a normal part of star formation.
What can we learn from looking at meteorites?
I've studied meteorites for pretty much my entire professional career. The reason, there are many reasons that make them interesting. We have meteorites from Mars, and we've never, we've never been to Mars with a spacecraft and brought rocks back. So having basically free samples of Mars is awesome. But the ones that I've always found interesting are basically the ones that are the oldest ones. So we've got meteorites that date from, or some of the elements of them, from the components of them, from even before the sun started to shine. So we can see all the way back to the processes that built planets, and I've always found that fascinating. Like how basically, how we got a solar system. They record all those processes.
So we'll go back, I guess, perhaps to a little bit of astronomy 101. What's the difference between a comet, an asteroid, a meteor, and a meteorite?
Right.
Apologies apologies, the question is a little bit beneath your level of expertise.
No, not at all. I mean, it's this is kind of thing that people ask a lot. And so a comet is an object that we can see is currently kind of degassing volatiles, ice, water, whatever, into space. So it's being, the solar wind is hitting it, and you get these particles, this volatile material coming off. An asteroid is an object where that's not happening. That doesn't mean it's not got ice in it. It just means we're not observing it doing that at that time. The meteorite is a object that if we knocked it off asteroid or a comet and it got through the Earth's atmosphere and landed on the Earth, then it's a meteorite. But it's basically the same composition. It's made it through the atmosphere. A fireball is the light that is given off by a big chunk of rock as it's coming through the atmosphere, not technically the rock itself. So there's all these kind of, finicky little classifications.
It's funny how they always tend to land inside craters.
They not always. Hopefully, if they're small enough, they don't make a crater, and that's good news for us.
What's a CubeSat, and what does it do? How's it different to the Optus D1 that we get TV from space from?
Right. So CubeSats are basically to get why this is a useful why these small satellites came into being. It's important to realize kind of how you launch a satellite and how it gets into orbit around the Earth. So basically, if it's a larger spacecraft, then that gets packed into what we call the fairing on top of a rocket, which is kind of the shield that protects it as it's going out of the atmosphere. And there's a special kind of system purpose-built to kind of blip that unique spacecraft, that bespoke spacecraft, off into space away from the rest of the rocket. And that's that whole structure around the spacecraft it's kind of finicky and expensive to build that brand new every single time. So the idea was that if we have essentially the same form factor for the spacecraft, and this is where these like CubeSats came in, which is really just a 10 by 10 by 10 centimeter basic unit, and then you can have a 1U, 10 by 10 by 10, and multiply that up. That there'd be standard sized racks that could fit on top of a spacecraft, on top of the launch vehicle, and blip those out into space. So it simply saves the cash that you would have to spend there to build a unique one.
And what can we use them for?
Well, I mean, people have tried to use them for a whole bunch of the same sorts of jobs as larger spacecraft. Whereas on a larger spacecraft, you might have a lot of different payloads doing a lot of different jobs. CubeSats are kind of good for doing, one thing reasonably well. They're much cheaper to build. They're much cheaper to launch. So then, if you're clever, you try and get as much possible payload space in that thing as you can, so you can have a payload, whether it's a camera or some other sensor, you can get it almost as good as what would go on a bigger satellite, which is much more expensive to launch.
And what are we using them for today?
Yeah, so you've got CubeSats. For instance, you've got a constellation of CubeSats now that's job is to image the entire Earth on a very regular basis. So anyone who wants to know it, so it's not like Google Earth. It's basically if Google Earth was updated every single day. So you had basically a kind of an image of the Earth every day. It's not quite there yet, but that's the concept. So you can build like much larger constellations than you would ordinarily with larger satellites, and kind of global wireless and things like that. Wi-Fi, sorry, wireless dates me a little bit. global Wi-Fi. You can do, people have used them for radar.
So compared to, say, your sort of Iridium satellite, but much more capable for things like the internet, that sort of thing.
Yeah, exactly. So really, there's kind of niches that they're really good in, and that kind of constellation is a really nice niche. That's one area that they're good for. Yeah.
What are the challenges? What are some of the challenges that we face when it comes to space exploration, other than, of course, including, of course, the prohibitively high costs?
Yeah, I mean, that it's a harsh environment, and so any spacecraft that kind of that gets out of the Earth's magnetic field, so our magnetic field protects us from solar radiation and cosmic radiation. You're in that's a hard radiation environment, and astronauts have to think about that if they go to the moon or Mars. But all spacecraft have to deal with that.
Even aeroplanes have to deal with it as well. Maybe to a lesser extent, but you can't fly too often.
It's at a much less. Yeah, if you're going up, even in low Earth orbit, it's a much more benign environment than if you're going to the moon. So if you're going to the moon, you need really seriously hardened electronics to cope with being bombarded by high radiation. So that's one thing, and then the other thing is really having systems that can operate intelligently without you having to kind of check them all the time. So great example of that was the NASA landing the Curiosity rover, right? Which was, this incredibly complicated engineering series of steps to get that big rover on the ground. And it was, really complex series of steps. The spacecraft came through the atmosphere, kind of had to steer itself. It had to drop off part of its shell to release the lander, and then what they call this sky hook that could kind of lower it down while it was firing retro rockets. And then because it couldn't drop onto the lander, it had to detach and kind of steer itself away. It was an incredibly complicated series of steps that basically all had to happen automatically. That's really hard.
So it could mean that in the future we'll be having, fewer unsuccessful landings.
Really the opposite.
So more things could go wrong, or?
No, sorry, you said we'll have
fewer unsuccessful.
Unsuccessful
landings.
That's right. Yeah,
that was
absolutely.
A bit of a double negative.
Exactly. Sorry, I'm not enough coffee. So yes, absolutely. So there used to be, NASA had a number of unsuccessful Mars missions. I think they're now on a run of the last 6 or 8 have been successful. So Mars is really hard, but it's they know enough now, and I like to say we know enough, but they've had enough experience now that you can kind of anticipate that they can hit most of the sort of critical issues. Yeah.
Why is Mars so much harder than the Moon, other than, of course, it's further away, obviously?
Yeah. So Mars is harder because it's got so for the Moon the Moon's not got much gravity, so you can if you've got a lander, then you can kind of pack in enough retro rockets to decelerate something, land on the surface, and you're not struggling to kind of keep it. The Moon's gravity isn't like dragging you down to crash it. The problem with Mars is that it's got an atmosphere, but it's so thin that actually it doesn't, unless you're quite a small lander, it doesn't help you an awful lot.
You can't use like a parachute, for example.
Right. So you can if it's small, but if you're bigger, then you need something more complicated. And it's just Mars is this kind of annoying little combination of stuff there. It's big, so it's got more gravity. It's got an atmosphere, so you can decelerate a little bit, but the atmosphere isn't dense enough that you can have parachutes that are big enough to land something big, blah, blah, blah. Yeah.
Why is Mars such a big focus for space agencies? Well, NASA in particular.
Yeah, I mean, so Mars is fascinating because it's, for so long, for like 150 years, people have wondered, okay, is there life on Mars, right? And obviously, way back when, people got quite optimistic about that. Well, if you're H.G. Wells, not necessarily optimistic, maybe, but we know now there's not, there's probably not been complex life on Mars, but there's still evidence that for a decent amount of time, Mars had equable conditions. That if you put terrestrial bugs on Mars a couple of billion years ago, they would have been quite happy. So the question is, did life arise independently on Mars? And having a yes or no to that would basically answer that question about, how lonely is the universe? If you have two independent, if life can arise in two places independently in our solar system, it means it's everywhere.
Do you see any Australian missions to the Moon or the Mars? What do you see the Australian Space Agency getting up to?
Yeah, definitely. So, actually, we're doing our own at the moment. So we have a program building our own CubeSats, which is going really well. We're launching our first one with a launch provider that's going to send it out of the International Space Station. That'll be happening either end of this year or early next. And that'll be building to a lunar orbiter in 4 or 5 years' time. So a CubeSat-sized lunar orbiter. And we've got we're working with NASA. They'll be hopefully delivering that to lunar orbit for us. And ESA are going to be doing mission control, which is really nice. So we've got a concept around that. We've also got industry collaborators on that proposal as well. So that's us. Hopefully the agency will be doing other missions as well. There's because NASA's got a program now called Artemis, which is going back to the moon, but the idea is going back to the moon to stay and then on to Mars. There's a lot more resources going to the moon, which includes the ability to kind of get ride along on NASA orbiters or NASA landers. So we can kind of get access to places that we could never get, 3 or 4 years ago. But now we can expect that we can get to lunar orbit without too much hassle.
Who exactly owns space? What can we do on the moon?
Yeah, no, so that's a really good question. There are a number of international treaties around, and obviously for a planetary scientist, this is kind of pushing the envelope of my specialty. But there's a number of international treaties around kind of ownership or non-ownership of heavenly bodies, whether it's asteroids or the moon. If it's for scientific use, then there's not an issue. We haven't really solved, but it's not. A lot of that stuff was from a lot of that legislation, that international legislation, was from the 60s. People really didn't think about that there would be kind of industrial applications, that we'd be wanting to mine asteroids. So there would be companies maybe that would be wanting to mine ice on the moon, convert it into fuel, and sell that fuel to NASA, right? No one had any of these concepts in mind. So a lot of people now are giving a lot of thought to how can we amend that existing legislation to give industry access to that,
It'd be quite interesting because when you dig stuff out of the ground in Western Australia, the government gets a royalty from it. And if someone goes space mining, what happens to that? benefits ultimately?
I mean, I think, like I say, like right now, so NASA can go to the moon and set up a base and mine ice and refuel their own rockets, and that's all fine. And anyone can do that. But owning any of it and selling any of it, there are international treaties around that, and I'm sure that some of that will be resolved in the next few years because there are so many opportunities there. It'd be bonkers not to.
Do you see us conquering Mars anytime soon?
I think so. I think it'll be the moon first. That's a sensible thing to do.
A bit closer, bit less out of the way.
And we built up a lot of kind of institutional knowledge with Apollo of just like how to do stuff, right? How to do stuff in space, learning kind of on the job. We lost all of that. So we've got to relearn all of that. You don't want to learn that and then be in a place where you have to wait 18 months to get home again. Much nicer to do it when you've just got a 3-day trip. So that's a much better place to learn.
Reminds me of a certain movie.
But right, exactly. But still, the same hard conditions, but the ability to kind of pull people out. But I think absolutely Mars next. Personally, I don't think we'll be able to answer the question of was there life on Mars, is there life on Mars without putting people there. We can send as many rovers as you like, but a human can walk in a day and look at more rocks than probably all the rovers that have ever been there.
Really?
Yeah, well, yeah. And because, it doesn't matter how many, if I'm walking around here, I'm like perfect pattern recognition system with a geology hammer and a hand lens. I have more resources than any rover that's ever been put there. Give me a little cart to trek around in, and I can, I'll see a weird rock over there.
Can't really do that with a rover. They're not quite smart enough.
No, and I don't think they ever will be. So a lot of people don't realize that Apollo was the most expensive set of missions that there's ever been. But in terms of kind of science output for a given mission, it was actually the best value for money. So so many papers came out of Apollo, so much knowledge came out of Apollo, and still is from the samples that the astronauts brought back, far more than on any other mission. So I think sending people to Mars, supplemented by with robotic assets, that's by far the best way to do it. And I think that'll answer the question. You've got people on Mars for 18 months. Main thing they're going to be doing, well, if I was one of them, is running around with a geology hammer looking for tiny fossils. Yeah, which would be awesome. I really hope that happens in my lifetime. I was born 3 months before the moon landing, so my old man actually did hold me up. Obviously those neurons aren't still connected, but I did see it. It'd be kind of nice to see humans land on Mars before I check out. Yeah.
Wait, so that means you were born in 66?
69.
Oh, 16. Oh, sorry, 3 months, not 3 years. My mum was born in 63, so she actually saw it in school.
No. So I have no memory of it.
Lucky.
But yeah, I did see it, with my eyes.
What is, feel free to issue a public call to action for more funding. Why is space exploration so important?
Space exploration does a whole bunch of things, and I think you can argue it from so many different angles. It's kind of the ultimate in collaborative international endeavors, right? So I do remember the docking of the Soviet spacecraft and a NASA spacecraft at the height of the Cold War, and the astronauts and cosmonauts shaking hands through that port. And that kind of thing, it's the International Space Station. There's a Russian module on there. Russian rockets have been launching astronauts into space through all of the tensions. And it's a great way of pulling governments and researchers together. I think there's nothing like space exploration for getting people excited, for inspiring members of the public, for that kind of a national pride achievement that makes people just stand a little taller that day, for getting students excited about doing science and engineering. I got into science because of the Apollo missions and Carl Sagan. It drives innovation. So we here at Curtin have an amazing team of PhD students and undergrads that are building our spacecraft, and they're super excited about that, because as well as the stuff we're doing with industry, with those spacecraft, we have all of those industry collaborations. We can pull them together in the end to have a science outcome, which is getting to the moon, and that the idea that you've got WA students that can do a degree and build a spacecraft that's going to get to the moon, that gets them pretty excited, and it should do. So I think for all those reasons, and I think that people don't realize is that that NASA spends, all those other agencies, every agency spends money on those missions for that kind of reason. It's for, it's to kind of further research, but it's not, if it was simply to make people like Phil Bland happy, then there wouldn't be $20 billion worth of assets orbiting Mars right now and on the surface. All of those spacecraft are built by space industry contractors. The instruments on them are mostly built by really advanced and capable engineering, university engineering teams. All those students go into jobs in space industries in their countries. The hardware that they build gets into those space industries one way or another. There's a return on investment that's like, I think you get ESA and NASA have calculated it. I think it's about, $5 out for every dollar in. So when people think that space, why are we putting money into space versus something else? It's actually a great investment in an economy, as well as all that other stuff. I'm obviously a big fan of the other stuff, but we make a lot of money out of investing in missions.
Gee, in this economy, that's a great return. And what are you working on now, research-wise?
Yeah, so we're doing a bunch of different things. I think we're doing a project with, actually an interesting kind of technology transfer one. We're kind of well known for a project called the Desert Fireball Network, where we track meteorites coming through the atmosphere, work out where they've come from in the solar system, and then where they land, we use these kind of really tough observatories that we can put out in the bush and leave for a couple of years without, and they just take images every night. Now it turns out that those observatories are actually really, really good for also tracking satellites, and that's a big deal so that we can get, in the end, some sort of space traffic control, so we won't have kind of a nightmare with overcrowding low Earth orbit or generating debris. So we've been working with Lockheed Martin for 3 years now on translating that knowledge from, tracking meteorites. I mean, you don't really get more blue sky than that, to something that is a great outcome for them, and hopefully, the world generally, if we've got a solution to tracking satellites. So that's one thing. then I'm really excited about the CubeSat program as well. I can't wait to get our first one up. I hope we've got enough money in the kitty so that we can take all of those students to the launch so we can see it fly. I think that would be great. And I've got to say, we're also doing a program called the Global Fireball Observatory, which is kind of expanding the DFN. Colleague of mine this is awesome. She's working on a computer, like intelligent system to count every single crater on Mars so that we can work out the age of the surface at really fine resolution. A bunch of my colleagues are analyzing material returned by spacecraft. One of my colleagues is on the NASA InSight mission, which is awesome. And I'm really excited about where we're going to go with CubeSat stuff and a lunar orbiter. I got to say, I do look at the moon a little bit differently now, because I know that we could get there, that we have the capacity to do that. So that's very exciting to me.
Thank you very much, Phil, for coming in and for sharing your knowledge on this topic.
Pleasure. Thank you.
You've been listening to The Future of, a podcast powered by Curtin University. If you have any questions about today's topic, please feel free to get in touch by following the links in the show notes. Bye for now.